Good afternoon. We're Group 18 and we're going to talk about the estimation of global heat transfer coefficient using CVD, KERN, and BELL-DELAWARE methods. This is the heat exchange project. Content. Today we're going to talk about the introduction, the materials and methods we used, results, analysis and comparisons, and finally conclude. Introduction. What is a heat exchanger? A heat exchanger is a device designed to transfer energy from one fluid to another through a solid barrier. There are two types of heat exchangers: concurrent, that gives a good heat transfer, and a cross-current that is more effective than the concurrent we mentioned. Also, there are three methods we use for modeling the heat exchanger. LTD, this is an ideal model, and there is no transfer of energy to the environment. The BELL-DELAWARE, that is a model designed for a tube and shell heat exchanger that gives an error of 25% and has correction constants depending on the geometry. And finally, the KERN, that is a standard model from 1950 that gives an error of 90% and has low temperature coefficients that are not reliable. Also, we use a tube and shell heat exchanger in CAD format that was given to us in the project. Here we can see the CAD. Also, we use thermophysical properties in polynomial values that were obtained in an online software to calculate these properties depending on the temperature. The properties we considered was density, specific heat, viscosity, and conductivity. Here we can see a graph where we graphiced the polynomial values that we obtained for the density versus the temperature for water, viscosity, specific heat, and finally conductivity. We also have to consider the thermal conductivity and other properties for stainless steel, which we consider constant because these values are constant for this range of temperature we're going to work with. Also, the two configurations that we talked about, contour and parallel flow, were considered in the CVD, which we use a cold flow 1 liter per minute, a hot flow of 3 liters per minute, and finally a hot fluid temperature varying from 45 to 55 degrees Celsius. Also, we had to choose the physics models of steady, three-dimensional, liquid, segregated flow, polynomial density, as we talked about, laminar because the Reynolds considered in the tubes are of this range, gravity and cell quality remediation. Finally, the methods we have to consider have some equations to consider the global transfer coefficient for clean and dirty heat exchanger, pressure drop in shell and tubes. These ones work with KERN, this one works with BELL-DELAWARE method, and finally LMTD method has some steps to follow in order to calculate first the heat transfer between fluids, then select the configuration to study, then calculate the logarithmical mean temperature difference, and finally calculate the overall heat transfer coefficient.
An acceptable cell quality varying from 0.6 to 0.8 was obtained. This means that our results can be studied. Temperature profiles in counter and parallel setups are almost the same. This is because the heat exchanger is small and the hot fluid flow is high. However, counterflow setup is expected to show a better heat exchange. Now, velocity profiles for both setups are the same. This is basically because the only variable that varies during our study was temperature. It's clear that there is a decrease in pressure for both the hot and cold fluid. As clearly seen, cold fluid's pressure dropped by a bigger margin in both scenarios than in counterpart. This is explained by the fact that the fluid in the shell is affected by factors such as friction, direction changes, expansions, and contractions. Simulation results shows clearly that counterflow setup has a higher and a lower temperature for cold and hot fluid respectively than parallel flow setup. The shell results for the KERN method shows that a laminar flow was presented. Also, because the Prandtl number is higher than 1, the momentum diffusion is higher than the heat diffusion. Nozzle equation for laminar flow were used and a small pressure drop was obtained. For the tube side, the only difference was that a higher pressure drop was obtained. Same analysis can be done for the BELL-DELAWARE method. As well as the KERN method, a higher pressure drop was obtained in the tube side than in the shell side of the heat exchanger. On the other side, the log mean temperature difference method results are shown. This method is an ideal model. In here, the heat transfer area or tube surface area was obtained assuming that pipe thickness is despicable. Then, having the heat transfer, the log mean temperature difference and the area, the global heat transfer coefficient was calculated. You should note that the log mean temperature difference method does not take into account any dimensionless number. Finally, the global heat transfer coefficients of the three methods used are shown. In here, it's easy to analyze that the KERN method possesses the lowest global heat transfer coefficient. Contrary to this, the log mean temperature difference method has the highest global heat transfer coefficient. Going further in the analysis, BELL-DELAWARE method differs in a 37% and KERN method in a 43% from the results obtained by the log mean temperature difference method. Conclusions: the counterflow setup enhances the heat transfer between fluids better than parallel flow setup. The pressure drop on the side of the casing is less than on the side of the tube due to interaction of the fluid with different factors such as higher temperature change and large flows. To comparing the KERN and BELL-DELAWARE method, it is concluded that the second method is more reliable because it has considered correlations of energy exchange between the fluids. The average error rate of the BELL-DELAWARE and KERN methods with respect to the log mean temperature difference method are approximately 37% and 43%.